here's my coin toss simulation. Start by importing random from random. So within my code I use coin toss. So I wrote that first. It calls upon CT to generate a random number, and if that number is below the probability of heads, it returns heads. Otherwise, it returns tails. So then coin toss, for each value, for each occurrence of n, appends to a list the resulting heads or tails, and then takes account of those occurrences within the list in order to give us the number of heads and the number of tails. Next, I set the parameters and created the files within main. So I start off with an accumulator for total flips. That shows up later. But I have the parameters for m, n, which is toss num, and the probability of heads. I then created a file for coin toss results, and then a file for error and relative error, making sure to open them with append rather than write, so that each occurrence in the loop does not write over the entire file. Next, I have my for loops for simulating this. So they are nested, so it starts off with the first value of n, which is 5. It then goes and grabs the first value of m, which is 1,000. And for each of those, it loops through each value of the probability. And within that, there's a toss accumulator, which will show up later. Creates a dictionary, and then for each possible combination of heads and tails within n, it creates an entry within that dictionary and sets it to 0. Then, with a range of m, 1,000 for the first one, it finds the heads and tails within coin toss for the first one, the second one, the third one. It takes that pair value, which would be the number of heads within the dictionary, and accumulates a 1 to it. And then also adds to the accumulator, and the total number of flips has n added to it. So after it runs through this code and the code that you'll see afterwards, which is within the same tab, after running through each probability of heads, it goes back and grabs the next value of m, 10,000, and then runs through that, and then runs through 100,000. And then it goes back to n and repeats the whole process, doing each probability of heads for each multiple of m. Next, we have the coin toss result file. This is just below what I just showed you, as you can see. So it starts off with a probability accumulator, writes out the format that this will be going in. Here I have it round to for the tails number, because I noticed that it was creating a float within the file, very long float. Then under heads, tails, and probability of event, it has a loop which goes through for each possible combination of heads and tails. It creates the probability of that heads within the simulation by taking the accumulated value of that number of heads within the dictionary and then dividing that by the toss accumulator, which is the total number of tosses within this set of parameters. The probability accumulator then adds that probability so that we end up with an entire sum of probabilities of 1 at the end. Each of these is written to the file, one after the other, creating a series and then finishing off that set within the file before going back and then looping with a different value of probability of heads, and M and N. Next we have the error file, which is just below that file, and it works very similarly. Same sort of setup, rounding and all that, probability accumulator. Has some extra values, as you can see, error and relative error. So it goes through a loop again for each combination of heads and tails. It takes the probability of heads, same thing, and also the probability accumulator. But for error, it takes the probability of heads and subtracts the resulting value from prob heads using n number of heads and probability of heads. So that goes back to these files, which were above main. These functions, sorry. And using tails and heads, it calls upon fact product, which calls upon factorial, which takes the factorial of each value, and DOS and heads and all that, and produces the numerator and denominator needed in order to produce a value for the probability of that occurrence. And this is not a simulated probability, but an expected statistical probability. So the error is then produced by finding the difference between those two down here. We then find the relative error by taking that error and dividing it by the probability of heads, blah blah blah, and multiplying that by 100 to get a percentage. Each of these is written just like the file before, and after the loop is done, it finishes up the file by giving us the sum of all probabilities. Looks like I left some extra code in there. I'll have to fix that. And finally, the whole program finishes by telling us the number of times a coin was flipped, which ended up being something like 37 million something. Way too many for a thumb to handle. So now I'm going to show you my code. So here's my code here. As you can see, here's CT and coin toss and the factorials and main, starting off with the parameters and the for loop and each printer. There we go. So if I run this, it will print the files within the folder that it's kept in. So running it. As you can see, they already show up, but they're not quite written yet because we haven't received that final print statement there at the end. And while we wait, I'll show you why I rounded up the probability of tails. As you can see in probability outcomes, you end up with not a very good looking probability of tails, which also doesn't make sense why it appeared, since probability of heads is nice and neat at 0.55. And it seems to happen for every 0.55. So the coin has been flipped 37,740,000 times, and the results have been printed to file. So we can check out these files now. So here are the coin toss results, formatted, and we get each one in series, doing each probability of heads first, as we expected, and then bumping up M to 10,000, and then 100,000, and then moving on to the next value of N, just as we wanted. And then next we have error and relative error. And so here has the same results, same probability of the event, but next to it is printed the error and the relative error. This did not turn out as neat looking as I like, but I could not figure out how to get it to not indent with the negative symbol. So as you can see, with the lower value of m, we get a higher relative error, which is to be expected. Probability graph is not as smooth. But then as we move up, we can go all the way to 50. So 50 tosses at 100,000 times per set of 50. You know, it's not too bad. We still get the odd, 54% off here and there. But for the most part, you can see general progression from a high relative error to a lower relative error. But as this is a simulation, it changes each time I run it. So, and then next, determining if a coin is fair. So I had a little trouble with this, but I decided that if you were in the real world would take a coin and you were to flip it, unfortunately, 1,000 times in sets of 5, you would be very tired, but you could take your recorded data of the number of heads and the number of tails for each of the sets, and doing your own accumulator, figure out how many times that occurred, and then divide it by the number of total sets. And whatever that probability ends up being, for each one, say you do 1,000 sets of 5, if it is a fair coin, you would expect that your probability would be close to this, and by close I mean within the error provided by our simulation. And if it's off, or it does not match at all, then you know you have a unfair coin. Alright, so that is my presentation. I don't think I left anything else. I'll see you tomorrow in class.